So quick overview. I'm going to start out by talking a little bit about machine learning and talking a little bit about machine learning and high energy physics. I'm going to talk a little bit. I'm going to introduce or perhaps review the theory of inflation. And finally, I'm going to talk about what I've done with the algorithm, the results, and some possible next steps. Okay, so to begin, machine learning and high energy physics. Now, I'm certainly not by any means the biggest expert on machine learning in this room today. But something that I have heard many times is that machine learning is essentially a black box. So, we understand what's going in to some deep neural network. We understand what's coming out. But as far as what exactly is going on in the interior is very mysterious. And in general, this is something that people are working to try to understand what's going on here better. But the upshot of this is that since we don't know exactly what's happening in the inner workings of a neural network, machine learning really works best when we have a clear measure of success. So think of things like, for instance, in the game of chess, computers can now easily beat humans. And this is an example where we may not understand exactly how the computer is valuing certain positions, how it's arriving at its moves. But we can see that in the end, it's beating us. So we know that it's working. Similarly, with self-driving cars, we may not understand exactly how the car is learning to drive, but we know what good driving looks like, we know what bad driving looks like, and we can look and actually see that, yes, the car really has learned to drive pretty well. Machine learning also works best when we have a good data set. So we need a large representative data set on which to train. So there's this famous example of handwritten digits where you can train a neural network to be able to decipher the digits between 0 and 9 with an accuracy of well above 90%. And of course, what's important here, right, is that you have a large data set. It has many different handwriting samples, and it has many examples of all of the digits so that the machine can actually learn over time to recognize the differences between all of them and the key features. If, on the other hand, you were to try to train a machine to learn all of the digits between 0 to 9, but you only showed it digits 0 and 1, or if you only showed it, say, the bottom left corner of any particular digit, obviously the computer would have much more trouble learning to distinguish these digits. Okay, all of this, I think, is very obvious. But the point is, when it comes to string theory, particularly when it comes to the string landscape, a big problem is that we don't especially understand the large data sets very well. There are some string vacua where we can compute a number of quantities, but in general, we can't compute all of the quantities that we'd like to know. So trying to learn all the features of a particular vacuum in the string landscape by machine learning is sort of like training a neural network and only showing it small parts of the particular numbers. Furthermore, the known string vacua, the ones that we actually understand well, are likely to be only a small subset of all string vacua, and it's very possible that they're a biased sample. So again, this would be like trying to train a neural network to learn digits, but only showing it zeros and ones. And finally, we don't have a clear measure of success. We don't really understand what does a typical vacuum in the string landscape look like. And so we don't, even if you can train a neural network to be able to, say, construct some string vacua, how do we know that these are actually representative of what the full landscape is? So the point is that machine learning is a very powerful tool, but at least within our field, at this point, it's largely a hammer that's looking for a nail. The hard part, I think, the hardest problem facing us is figuring out problems within the field of high energy theory that are going to be amenable to a machine learning analysis. And based on what I've said so far about when machine learning is most successful, I think that the key is that we need to be able to find problems that we already understand fairly well so that we can train a computer to reproduce our results and then perhaps even make some new predictions, do things even better than we can. So there are a number of areas where this where you could maybe do this. But one that might be good in this regard is the theory of inflation. And inflation is nice because it's something that we actually have some experimental data for. And this experimental data is actually strong enough to rule out some models that you could write down of inflation. On the other hand, neither the experiment nor the theory is strong enough to pinpoint a single model of inflation. There are many models of inflation that are consistent with the experimental data, and at least from the perspective of theory, it isn't immediately clear which of these models are going to be better than others. So the idea, what motivated this project is, perhaps we, as humans, cannot figure out what exactly the best models of inflation are, but perhaps machines could be helpful in this regard. And machines could give us an idea of which models are more likely in some respect than others. And in this way, could perhaps even make predictions for forthcoming inflationary experiments. Okay, so this is the idea. Let me start out now by giving an introduction to the theory of inflation for the non-experts. This will be very boring for the experts in the audience, but hopefully it'll be a nice review. So inflation is a theory that describes the very early universe. According to inflation, in our very early universe, the universe was expanding exponentially. So here's time, and here's the scale factor, which measures the size of the universe. And what happens is that at the beginning, you have this exponential growth of the universe, which at some point ends, and we transition into a phase of radiation domination. Inflation is nice because it solves a number of problems that plagued the old standard model of cosmology. And in order to solve these problems, you need for the universe to expand by a factor of about e to the 60. So the scale factor at the end of inflation has to be about 60, e to the 60 times larger than the scale factor at the beginning. And so you frequently hear the phrase 60 e-folds of inflation, where the number of e-folds here being this ratio here. So that's from cosmology, what inflation is. From a field theory perspective, inflation can be thought of to very good accuracy as simply the theory of a ball that's rolling down a hill with friction. So in this analogy, the role of the ball is played by this scalar field phi, which is called the inflaton. The hill is played by the potential v of phi. And then the friction comes from the expansion of the universe. It's what's known as Hubble friction, and it gives you this friction term here in the equation of motion for the scalar field, which you'll see is effectively just ignoring this term here, just the equation of a gradient descent. The friction term here, the Hubble constant, is simply equal to the energy of the ball. So this is the kinetic energy plus the potential energy. Now, successful inflation, that is exponential growth of the scale factor, occurs when the kinetic energy of the ball is dominated by its potential energy. So V is much larger than phi dot squared, and you furthermore need for the second derivative of the ball to be dominated by the friction term and the gradient term in the equation of motion. The conditions for this to occur can be translated into conditions on the shape of the inflationary potential. So in particular, to get a slowly rolling field, you need for the first derivative of the potential and the second derivative of the potential to be small, normalized by the size of the potential itself. So this is encoded in what are called the slow roll parameters epsilon and eta, respectively. And so the condition that you get inflation is the condition that these two slow roll parameters are both much, much smaller than 1. These slow roll parameters can be related to cosmic observables, so things that you can actually go out and measure with telescopes, looking into the far regions of the universe. And so the tensor to scalar ratio and the spectral index, NS, are sort of the two observables that will be important for us today. You can see that they're related very simply to these slow roll parameters, epsilon and eta. Now, you might ask, where exactly are we supposed to evaluate these things? Because after all, we have an entire potential, and you can compute the first derivative and second derivative, and therefore the slow roll parameters everywhere. And the star here is to remind you that we're evaluating at horizon crossing. So this is roughly 60 e-folds before the end of inflation. So the picture then looks like this. We have a potential that looks like this. Inflation will end when we get close to a minimum of the potential. And most of the inflation will occur when the potential is very flat. So near a plateau of the potential is where the 60 e-folds will be generated. So we can actually compute how many e-folds will occur between a given location phi star and the end of inflation, phi end, by simply integrating this function here, 1 divided by the square root of 2 times the first slow roll parameter. And so by setting this to 60, given any potential, we can invert this formula and compute the field value phi star, which gives us these 60 e-folds. And then at this particular field value, we can compute the first and second slow roll parameters, and from this, compute the inflationary observables. So the upshot of all of this is that simply if you give me some inflationary potential V, which looks like this, there's this nice algorithmic way to compute cosmic observables by first computing the number of e-folds of inflation, and then at the place where this is 60, computing the tensor to scalar ratio and spectral index. One last point on inflation is that models of inflation can be generally sorted into one of two classes. Large field models have the property that the field moves a distance greater than 1 in Planck units, and small field models have the property that moves a distance smaller than 1. Okay, so from what I've said, the potential is really the key to inflation. Given some potential, you can compute the cosmic observables. The problem is that the exact potential is not known. So here's the data. This is actually the 2015 data on the spectral index, also called the primordial tilt, and the tensor to scalar ratio. And you can see here, for various experiments, the 68% confidence interval is shown in the solid color, and the 95% confidence interval is shown in the lighter color. And overlaid on this are the predictions of various models of inflation. So here up here is the cubic model, which you can see is ruled out in more than 95% confidence. But there are many other models down here, the natural inflation, linear potentials, the Hilltop quartic model, et cetera, which are all compatible with the data. So the goal, what we really like to have from both an experimental and a theoretical perspective, is a reason to select some models over others. We'd like to narrow these bounds down experimentally, and as theorists, we'd also like to have a reason why certain models here might be favored over others. Now, in string theory, we expect, of course, that we're going to have this vast landscape. And in this vast landscape, it's likely that many different models of inflation are going to arise. So we're going to have many possible different models. What this suggests is that we'd really like to take a statistical approach to figure out, of all of these possible inflationary models, many of which could occur in the landscape, which ones are going to occur with the greatest prevalence. Now, of course, to really do this properly, we need to have a detailed understanding of string vacua, so an analysis more like what Cody was talking about this morning. But given our relative lack of understanding of the string landscape, the first thing that we could think about doing is perhaps using a simple random matrix or some sort of random inflationary potential approach, so that we randomly generate these inflationary potentials and see what sorts of models, what sorts of observables we expect to get. So various approaches have been considered to randomly generating inflationary potentials, Dyson-Brownian motion, Gaussian random field, et cetera. The goal of this talk, though, is to try to consider a new approach which is motivated by machine learning. And so with that, finally we get to the algorithm learning to inflate. So the idea here is very, very simple. First, what we're going to do to begin is to initialize our inflationary potential by expanding, by Taylor expanding it with random coefficients. So we Taylor expand the potential here. We have these coefficients Ci. We start at I equals 2. And what this does is that it enforces that we have a minimum at the origin for which the potential vanishes. And so we're going to say that this is where inflation ends, is near the origin. Now we also have these two energy scales in the problem. This vertical scale, lambda v, sets the height of the potential, and the horizontal scale, lambda h, sets its width. The vertical scale isn't going to show up in the observables we talked about, the tensor to scalar ratio and the spectral index. So for our purposes, this is boring, and we're essentially just going to neglect it. What's interesting, though, what's more interesting is the horizontal scale, lambda h, which is going to tell you whether you have a small field model or a large field model, how long this field has to roll to give you sufficient inflation. So what we're going to do to begin is we're going to absorb this lambda h into the definition of phi by this rescaling, defining phi tilde simply equal to phi over lambda h, so that our final form looks like this. Now, we're just going to randomly draw these Taylor coefficients at the beginning. We'll say that they're normally distributed and independent. You could, of course, consider other possibilities, but we'll start with this. So we take these to be normally distributed with mean 0 and variance 1. The variance here is actually not important because we can always rescale that or reabsorb that into this vertical scale lambda v, which we're neglecting. The mean, of course, is important. And in particular, if, say, C2 is negative, then we would get a local maximum rather than a minimum at the origin. And that's bad. We don't want that, so we're going to throw those out. And we're going to insist that our potential must be monotonic on the range from 0 to 0.5. We choose 0.5 as the initial value in order to maintain perturbativity. In other words, we want these successive terms in the Taylor expansion to be getting smaller. And so for this reason, we say that they can't get any larger than 0.5. And then it turns out that setting n equals 15 is perfectly fine for these, for our purposes. Okay.
Sorry, could you talk about the monotonicity again?
Yeah, so
you generate a bunch of things and you just the ones that fail.
That's right. Yes. The upshot of that is that this isn't quite right because we're only keeping monotonic things, right? So in the end, there will actually be things won't be completely independent, but that's the idea. Draw them independently, throw out the ones that don't give you monotonicity.
You're drawing from some modified distribution that is generated in exactly this way.
That's right. Okay, good. So so what happens when you do this? So this is the first step in the program. Well, what happens when you initialize the potential in this way is that it will typically be very steep. So it will typically be a quadratic or even steeper. And models like this will only give you sufficient inflation if the field rolls a very long distance. So in particular, you need for phi to roll a distance of about 15 or 20 in order to get 60 e-folds of inflation. So this will give you a large field model of inflation. And now what we want to do, starting from this, is we want to figure out, can we build models that will give us more inflation? Or another way to say this, can we build models that do not require such a large traversal, but can have a smaller horizontal scale lambda h? And the way we're going to do this is by using effectively very simple machine learning techniques. So in order to get a model with more e-folds and smaller lambda h, we're simply going to treat these coefficients as weights in a single layer neural network. And we're going to use gradient ascent to maximize this tilted number of e-folds, which is simply ne divided by the horizontal scale lambda h squared. This ne tilde here is simply what you compute if you use our formula for e-folds using this tilted potential right here. So this is obviously from the perspective of machine learning, extremely simple. Perhaps doesn't even deserve to be called machine learning. All we're doing is training these weights here in a single layer network. But for our intents and purposes, this is all that we need to do. So we can ask, as we train these things, is to maximize the number of tilted e-folds, what sorts of models do we get? Now, on the machine learning side of things, from the perspective of the gradient descent, this is a perfectly clear algorithm. We're simply maximizing this NE tilde. But from the perspective of the inflationary phenomenology, we can interpret this in two different ways. One of them is that we can imagine that we fix the number of e-folds to be 60 and are minimizing this horizontal scale lambda h. Alternatively, we could fix lambda h and maximize NE. Again, from the perspective of the gradient descent, they're exactly the same. The gradient descent doesn't care which one we do. But given some model, if we want to take that model and compute the phenomenology, it actually matters which of these approaches that we'll take. And we'll see that shortly. OK, so that's the idea. Very simple. What do we get? So first of all, how does the learning process work in practice? We saw that when we initialize the potential, it tends to be very steep. It's actually steeper than a quadratic. And as a result, you need to take the scale lambda h very large, of order 35 or so, to get 60 e-folds of inflation. Now, when you perform this gradient descent on the coefficients, the first thing that happens, of course, is that the potential flattens out, because flatter potentials give you more e-folds. And so here you see we go from this potential, which was steeper than a quadratic, to at some point we get effectively a linear potential, which has a slightly smaller lambda h. As we keep going, the top here starts to fold over, and eventually we get a local maximum, or what's called a Hilltop model of inflation. Now, as we keep going, you see that the scale lambda h starts to decrease rather drastically. And in fact, here we have a good interpretation physically of what's happening when we get near the maximum of this gradient ascent, is that the maximum of the gradient ascent corresponds to taking this field closer and closer to the maximum of this potential. So in fact, when we get to the very maximum, this field is just at the maximum at the very top of this hill. In that case, we'd actually get an infinite number of e-folds, because classically, this field will just stay at the top of the potential forever. So what happens is you perform the gradient descent, the ball gets closer and closer to the top. If you haven't chosen your learning rate exactly right, what will happen is that at some point, you'll overshoot the maximum. And this ball will literally overshoot this maximum. It'll be on the other side, and now we no longer have a monotonic potential. So instead of rolling down to the minimum here at the origin, the ball will roll over to the right instead. And so in that case, at that point, we stop the gradient descent. So this is what happens. In fact, this is what happens about 90% of the cases. We develop a local maximum like this. The other 10% of the time, we develop an inflection point. It should be known that all of the models we've seen so far are actually very commonly studied in the inflationary literature. The quadratic models, linear models, Hilltop models, and inflection point models are all things that are well known to inflationary people and have been well studied. So now we can study the particular phenomenology of the Hilltop versus inflection point models that we're seeing. We'll start with the Hilltop models. So recall, our gradient descent gives us a trajectory in the space of all inflationary models. This then translates to a trajectory in the space of cosmic observables. And their trajectories look like this. So at the beginning, we have a very steep potential, which gives us a large field model of inflation, and hence a large tensor to scalar ratio. So we start somewhere up here. As we learn to inflate, the tensor to scalar ratio shrinks. You can see that at the beginning, the spectral index starts to get larger, but then eventually it shrinks as well. The first thing to note is that these trajectories do actually pass through the exclusion limits. So here's the 2 sigma and 1 sigma exclusion regions, and you can see that indeed we do get successful phenomenology. The models do actually pass through the regions that are allowed by observation. So the model, the machine is actually learning models of inflation which actually agree with experiment, which is nice. Something to note, though, is that all of these models, which give successful phenomenology, are large field models. If you look at the scale lambda h, in which all of these trajectories exit the 2 sigma exclusion region, so along this left edge right here, you find that the typical value of lambda h in which this occurs is between 20 and 30. And in fact, in no examples out of the 10,000 simulations did we have one where lambda h was smaller than 1. There were a few where it was pretty close to 1, but nothing smaller than 1. So all of the models here that considered that gave successful phenomenology required lambda h to be large.
Does that tell you something about your bias, because there are small field models that are consistent with data?
That could be, yes. So one interpretation is that it could be that the initial conditions that we picked need to be modified. Another possibility is that instead of looking at the Hilltop models, you should consider the inflection point models. So in the inflection point models, what happens is that so when the model learns an inflection point, the shape of the potential looks like this. Of course, this is just the equation of an inflection point. The quadratic term vanishes at the inflection point, and so we just have these 3 terms here, plus some higher order things which aren't so important for us. Now, as you know, successful inflation occurs when the potential is very flat, which in this language means that both the first and second derivatives are small. The second derivative, of course, vanishes at the inflection point. So in order to get successful inflation, what you want is for this W1 to get small. So that's what you expect, and indeed that's exactly what gradient descent does. If you feed in some inflection point model like this, what will happen is that W1 will just shrink closer and closer to 0, and W0 and W3 and all the higher order terms will be effectively constant. What this means is that no matter how small your scale lambda h, as long as your learning rate is chosen appropriately so that W1 goes to 0, if you wait long enough, W1 will get sufficiently small that you will get a successful small field model of inflation. No matter how small lambda h is, you just have to take W1s even smaller. And in this case, what will happen is that you can always find some value of W1 for any lambda h such that you actually get good phenomenology. Note that here we actually had to take the approach of fixing lambda h and letting NE be maximized. If you try to use the first approach for inflection point models, you'll actually get some very bizarre results, which I could talk about later, but the details probably aren't so interesting. Okay, so that was the single field case, where we had just a single field and we had a Taylor expansion in a single variable. The other thing we can do is generalize to multiple fields. After all, we expect from string theory that our universe likely doesn't just have a single scalar field. It probably has many scalar fields. And so models of inflation could very well involve of order 10, 100, or maybe even 1,000 scalar fields. So the very first step in going from 1 scalar field to 1,000 scalar fields, of course, is going to 2 scalar fields. So what happens if we write down a 2-field model? And we have, so now we have Taylor coefficients for these 2 fields, and we try to maximize and see what sorts of models of inflation do we learn. So what happens here is that at the very beginning, when you initialize the potential, you'll have a hierarchy in the masses of the 2 fields. So what that means is that one of the slopes will be much steeper than the other one. And so what happens during inflation is that you first roll down the steep slope, and then once you've done that, you roll down the slope that isn't as steep. And so in figure A, you can see that this is what's happened. At the beginning, the field rolls down this steep slope, and then at the end, it rolls down this not so steep slope. And that's why there's this curve right here in the field space of phi 1 and phi 2. Now the first thing the gradient descent does is that it evens out this hierarchy. It gets rid of the differences between the slopes. And so as a result, the model that you get is effectively single field. You're inflating exactly in this diagonal direction. And once you get into this single field regime, gradient descent does exactly what we saw it did in the single field case. You start out with this quadratic potential. It eventually flattens into a linear potential, and that eventually flattens into a local maximum, a Hilltop model. And what you might have thought is that it would just sort of stay there forever. That once you go from two field to an effectively single field model, that it would just remain an effectively single field model forever. But in fact, when you let the gradient descent go further and further, eventually the model actually becomes multi-field once again. And you start to see significant curvature of the inflationary trajectory in field space.
By this you mean train it for more and more epochs?
Yes, yes.
So there's a local maximum that you're finding that's single field, but then you find you get even more e-folds in a complicated multi-field model.
Right. So yes, so in this case there's a nice intuitive interpretation of this, which is that single field models, if we consider the reward function ne tilde, single field models represent a saddle point in the space of all of the models. So what happens is that you initially, right, you have some two-field model. What you initially do is you move, gradient descent pushes you along the stable manifold closer and closer to the saddle point, which is the effectively single-field model. And if the model were exactly symmetric, of course, nothing would ever break that symmetry. So gradient descent would just push you towards a hilltop, and you would remain on this stable manifold getting closer and closer to the saddle point, which is this single-field hilltop model. But if you're not exactly on this stable manifold, eventually what will happen is that you'll exit along an unstable manifold. And so you'll go away from the saddle point, and that's what's happening down here, is that at the end you actually learn these legitimately multi-field potentials.
How do you know it's a saddle instead of a local maximum?
If we're a local maximum, then for the gradient descent, it would be a sink, right? So once you get close to it, you just sort of go towards it forever. But because you don't, because you leave, what that's telling you is that there must be some direction in this space of all models that you're exiting, so that the gradient descent is actually taking you further and further away from it once you get close. So you start out going close to it, and then you get further away from it.
Yeah, I guess I'm doing it the other way where it's a min, but couldn't stochasticity drive you out of a local minimum to a better one? Or?
Yes, but in this case, there's nothing stochastic about this gradient.
Using gradient descent, not stochastic gradient.
Right. I mean, all we have is this function ne tilde of these coefficients, right? It's a perfectly deterministic thing. We're just performing gradient descent.
You're really using gradient descent, not stochastic gradient.
Yeah. You'll note I never use the term stochastic gradient ascent in this talk for a reason. Yeah.
I just assumed.
Yep. Yeah. Right. Yeah. Okay. So that's one interesting thing. Another interesting thing is that in the two-field case, we can actually observe far more exotic models of inflation than we saw in the single-field case. So you recall in the single-field case, the endpoint of the gradient descent always ended at either a hilltop model or an inflection point model. And that's all we ever saw. But in the two-field case, in rare instances, what you actually find are things like this. So this particular potential, you see, plotting the potential as a function of the distance traveled, has not one, not two, but actually three plateaus. So it's sort of like having three inflection points superimposed on each other. And if you look how the field moves in field space here, you see that it actually initially starts out going away from the minimum at the origin, but at some point it hits a wall and curves back, and then curves back all the way down here. So unlike in the single field case, we actually are observing some rather exotic models of inflation, and it would be interesting to study these things further. So let me summarize. We used gradient ascent in the space of Taylor coefficients to maximize the e-folds of inflation. We found large field Hilltop models and small field inflection point models that actually gave us viable phenomenology. Phenomenology that agrees with experiment. And in the two-field case, we eventually learned genuinely multi-field models of inflation that had significant curvature. And we saw that in some cases, these could have much more exotic behavior than the single-field case. Okay, so this was certainly a very exploratory study. There's, I think, many things that could be done. One thing, I mentioned that the potential is really the key to inflation. This was actually a lie, because you can also consider not just modifying the inflationary potential, but also modifying the kinetic term. So in string theory, for instance, there's a famous example. You have what's called the dBi action, which gives you a particular form of the kinetic term. And people have actually studied and generated models of inflation that depend on this dBi action. So it'd be interesting to see if we allow not just the potential term, but also the kinetic term to vary, might the model actually learn dBi inflation or something like that, or perhaps it might learn some other form of inflation with a non-trivial kinetic term that we haven't yet studied in as great of detail. Of course, it's very important, I think, to understand what happens in the many-field case, so considering more fields, and also moving beyond the slow roll, slow turn approximation that we used here. Now, the difficulty with this, with adding more fields, is that the number of Taylor coefficients in a multi-field model grows exponentially with the number of fields. On the bright side, we only considered very simple machine learning techniques, namely simple gradient ascent in a single layer neural network. But perhaps in the more field case, it would prove fruitful to consider more sophisticated machine learning techniques and more sophisticated network architecture. You could also consider other reward functions. We sought to maximize the tilted number of e-folds, but you could consider other reward functions as well. And finally, perhaps you could combine this with other approaches to random inflation and use this to find new models of inflation or learn more things about them. So thank you.
Thank you very much, Tom. Are there more questions for Tom?